right, guys, we are going to get started in chapter 6. Let me just present my screen so we can start. Okay, so in chapter 6 for lesson 6.1, it's a 2-day lesson. This is day 1. We're going to talk about exponential growth and decay functions, which you should be familiar with not only from Algebra 1, but from science classes. All right, our goals today are to evaluate, graph, and interpret equations. Okay, so to start, we have our exponential function, y equals a b to the x. All right. The hint that it's exponential is that the exponent is a variable, or there's a variable up in the exponent. All right. So A represents your initial amount, and B represents your growth or decay factor. All right. For your exponential growth functions, the A value cannot equal 0 and the B value cannot equal 1, but must be a positive real number. All right. Now, when your B value, if your B value is greater than 1, okay, since B represents growth decay factor, when B is greater than 1, that represents exponential growth. If B is less than, I was going to write D. If B is less than 1, that represents decay. All right, so a quick sketch of exponential growth. You're going to have a graph that looks like this, growing exponentially. All right, and then exponential decay would look something like this. Okay, if not transformed, so if there's no transformation, shifting right, left, up, down, stretch or shrink, something like that, if not transformed, the x-axis is an asymptote. Oh, hold on, that's really sloppy. And since that's a new word, I should probably write it a little cleaner so you know how to spell it. Sorry about that. All right. So it's asymptote. All right, which means the graph gets very close to the x-axis without crossing. So you can see in my sketches, all right, the graph gets very close. It kind of like hugs the x-axis, but it never touches it or crosses it. And we call that the asymptote of the function, okay? All right, so that's the basics of exponential functions. Let's move down to see what's coming up next. All right, here it says, tell whether each function, represents exponential growth or decay, then graph it. All right, so we're going to use our graphing calculators to graph these. So let me, I forgot to pull my graphing calculator over. So let me pull that over real fast. Sorry, it's taking a second. All right, there we go. Pull this window back up. Okay, so for your equation, you're going to graph it. Let me clear this out. And actually, let me reset because I don't know the last thing I did on the calculator. So second plus 712. We'll just kind of reset and clear everything out. So I'm going to go to y equals, and I'm going to type in the function just as it is, 1.3 raised to the x. I'm going to hit graph. All right. Now we're supposed to tell whether each function represents exponential growth or decay. We can determine that by the b value. We can also determine it looking at the graph. Okay. You can see that the graph is growing exponentially. So it's exponential growth. We also know it's growth because the b value, 1.3 is your b value. The b value is greater than 1. Okay. So we'll write both of those things down. All right. So the b is equal to 1.3. Since b is greater than 1, it's exponential growth. Now to graph this, since again, like I said, we're using our graphing calculators, I'm going to go over to the table, it's the second table, and I want to write down some of these values, okay? And I'm not going to write them all down. I may not even use all of them for graphing purposes, but I'll start with -2, and that's approximately 0.59, come on, 0.59. Then we have -1, which is approximately 0.77. Then we have 0, which is a 1, and 1, which is 1.3, and then 2, which is 1.69. Okay, so those are the points that I'm going to use for graphing. All right, so then you would just plot each of those points approximately where they belong, which you guys know is going to kind of be hard for me with this, but I'll do my best. -1, that's up a little bit more, then 0, 1, then 1, 1.3, and then 2, 1.6. All right. Now we know because we saw the graph on the calculator what it's supposed to look like. So you just kind of shoot up after you go through that last point and you're hugging the x-axis, which is your asymptote. Okay. All right. So we're going to do the next one the same way using our graphing calculators. Take note that the b value is equal to 1/3. Right? We're in the form y equals a b raised to the x. So the exponent is attached to the b value. The b value is 1/3. Since b is less than 1, we know that this is decay. All right, we're going to go to our graphing calculators to get some points for graphing. So let me pull that up. All right, so let's y equals, clear this out. We're going to have 1/3. Oh, that's not what I wanted to do. Sorry. I keep pushing the wrong button. There we go. 1/3 raised to the x. Oh, goodness. X. Okay. And then hit graph. And you can see it's decay. And I'm going to hit second graph to get to the table. All right. And just like we did before, we'll write some of those coordinates down. Or there's my table that I set up. So I have -2, 9, -1, 3, 0, 1, 1, 1/3, 2, 1/9. Okay, and that should be enough for graphing purposes. All right, so let me get rid of my calculator. Okay, so now I'll plot those points. -2, +9. Well, that's off the grid just a little bit. That's 7, or 6, sorry, 7, 8, 9. So like somewhere up here. Then we have -1, 3, 0, 1, 1, 1/3, and then 2, 1/9. So it's getting closer and closer to that x-axis. It's hugging it. It's its asymptote. All right, we know it's exponential decay. We know what it looks like because we saw on the graphing calculator. So I'll go ahead and sketch that. All right, so keep in mind, or maybe take note to these 2 points here. Oh, no, I'm sorry, not those 2 points. Sorry, I was circling the wrong thing. Let me erase that. So it was 1.3, and 2, 1.69. All right, the point I was supposed to circle, or the 2 points, are these two. All right, when graphing exponential growth and decay models, you're always going to want to use 0, 1 as one of the core points for graphing, and 1b. Okay, 0, 1, notice it's here as well, 0, 1, and then 1b. Okay, 1, if you plug in the value 1 for the for the exponent, the variable, then the y coordinate or the y value is going to be the b value, which is 1.3. So 1, and then this is the b value, 1, and then 1/3 was the b value. So those are two good points to always kind of keep in mind when graphing. Okay. All right. The exponential models. So we have y equals a 1 plus r raised to the t, and y equals a 1 minus r raised to the t. So the only difference is you're replacing b with 1 minus r or 1 plus r, depending on if it's growth. This is your exponential growth model, and this is your exponential decay model. All right. The 1 plus or minus r is the growth or decay factor. R is the rate of decrease or increase. So again, you're replacing b, right? Instead of y equals a b to the x, you're replacing b with 1 minus r or 1 plus r when we're talking about exponential decay or growth models. And then the variable x turns into a t because we're always going to be talking about the time in which something is decaying or growing. Okay. So we're going to be using those next. Let's keep on moving along. All right. So given the equation y equals a times the quantity 0.5 raised to the t divided by 13, find the decay rate. All right. So what you want to do here is we want to manipulate using rules of exponents and simplifying. We want to change the, oh goodness, don't start. Sorry, guys, my pen. My pen gonna work? No, it's not gonna work for me. Let me just turn my board off and turn it back on. All right, so let me talk through this as I'm trying to get my board to work. You want to manipulate this equation to get it to match the exponential growth models that I just showed you right above, okay? So instead of t divided by 13, you want the t value to be by itself. You don't want it to be divided, oh, there we go, divided by 13. So, all right, so what I'm going to do is I'm going to first start by writing just the equation again. Y equals a quantity 0.5 raised to t divided by 13. Okay. Then I'm going to use the power of a power rule to rewrite this as y equals a. And then inside of my brackets, I'm going to have 0.5 raised to the 1/13th. And then that raised to t. Okay. So that's called power of a power property. So remember, we are just rewriting from one step to the other, but what I write in the next step needs to be equivalent to what's above. And because of the power of a power property, I can multiply these back together. 1 over 13 times t, right? 1 over 13 times t is equal to t over 13. And that was originally what I had, okay? So every time you move on to a new step of this problem, what you're writing needs to be equivalent to what's above. Okay. Now I'm going to simplify. I'm going to actually take my calculator and do 0.5 raised to the 1/13th and turn this into a decimal. So let me grab my calculator. All right. So I'm going to have 0.5 raised to the 1/13th. And then I push enter. Okay, I am going to round this, but I'm not going to round it yet. Okay, so I am actually going to write all those values down, all those decimal places down. All right, so now I have y is equal to a, and then inside of the brackets, or you can change it to parentheses, it's up to you at this point, you're going to have 0.9480775 raised to t. Again, this new line is equivalent to what's above, okay? All right, so, and all I did there was I evaluated the power, the exponent. All right, so then what I'm going to do is write this as either 1 minus or 1 plus some number raised to t. Okay. Since the number inside the parentheses is less than 1, I know it's exponential decay, and that means it needs to be 1 minus. All right. Keep in mind too. Oh, I kind of erased that. What number was that? That was an 8, 0. Yeah. All right. Keep in mind what I write in this next line needs to be equivalent to what's above. So in parentheses, if I have 0.9480775, I need to subtract something from 1 to get that decimal. So what do I need to subtract from 1 to get this decimal? Well, to do that, I can use my calculator and I can do 1 minus, and I'm going to grab that decimal above. So if I subtract 0.051922488, 4857, if I subtract that number from 1, that gives me the decimal 0.948, so on and so on. Okay. So I'm going to write that down. And at this point, I am going to round. So I'm going to round it to 0.052. Okay. All right, so what I'm left with, I'm going to erase all this and just write my final. I have y is equal to a times the quantity 1 minus 0.052 raised to the t. So now this matches that y equals a times the quantity 1 minus r raised to the t, which means this is decay, right? Exponential decay. It also said it was decay. We're trying to find the decay rate. All right, so the decay rate, that R value, okay, well, the R value is 0.052, but we're going to give it in a percentage. Okay, so the decay rate is 0.052. In percentage form, move the decimal 2 places to the right, so it's 5.2%. And this is an approximation because we did round that decimal. Okay. All right, so that was that problem. Let's look at the next. Okay. Real world problem. It says the value of a car. Oh, that's supposed to say car with a R, not a Y. Let me fix that. Okay. The value of a car Y in thousands of dollars can be approximated by Y equals 31 times the quantity 0.92 raised to t, where t is the number of years since the car was new. Okay. So looking at this, you should be able to tell me this is the A value, 31. That's the initial amount. Okay, that means that the car was originally priced at 31,000, right? In thousands of dollars, so $31,000. The B value is 0.92. All right. So we know it's exponential decay. A car decays in value as soon as you drive it off the lot. And T is the number of years since the car was new. Okay. So is it growth or decay? Well, I already kind of answered that. Where's my mouse? Sorry, guys, nothing is working properly for me. Okay, there we go. Is it growth or decay? This is decay. And how did I know that? I know that B is equal to 0.92, and when B is less than 1, it's decay. All right. Rate of growth or decay. Well, that now is the R value. So we have to think about inside the parentheses, instead of it being B, I need to convert it to 1 minus R. All right. So 1 minus R is equal to what's inside that parentheses, 0.92. All right. So I can solve for R, subtract 1 from both sides, then divide by a negative. So R is equal to 0.08, which is 8%. All right. So the rate of decay is 8%. Then it says, when will the value of the car be $9,600? All right. So where am I going to plug that in? Y or T? Well, it's not the time, right? That's what we're looking for. When? We're looking for the time. When will the value of the car be 9,600? So I'm going to plug 9,600 in for Y and set it equal to 31 times 0.92 raised to the T. All right, so we could divide both sides by 31, but then we'd actually be stuck. We have not yet learned how to solve equations that have variables up in the exponents. That's actually what we're going to be learning to do in this chapter, but we don't know how to do that yet. So for now, we're going to use our calculator. And you're going to look to see when when Y is approximately 9.6, right? We want to get as close to 9.6. What is X? Okay, X is going to be your time on the calculator. Okay, so let me pull up my calculator. All right, so I'm going to graph this function. So the function is 31, then parenthesis, 0.92 raised to the X, and you're going to graph it. Okay. Then what you're going to want to do is hit the button trace, and you're going to want to trace. So I'm just using my arrows right on the calculator, my right and left arrows, and I'm looking for when is Y about 9.6. I'm going to keep scrolling. I'm looking at this value here. When is it close to 9.6? Because that would represent $9,600. Oops. Oh, did I go too far? Sorry. I was going the wrong way, not even paying attention. Oh, like something doesn't make sense. Look at my graph or look at my equation. I didn't type it. It's 31. I guess I didn't push that 1. 0.92 raised to the X. Let's try that again. Because I was like, that is not working out the way it's supposed to. Oh my goodness. I'm just going to clear it all and try again. 31 parenthesis 0.92 raised to the X. I don't know if it's me or if it's why I'm having trouble hitting the right buttons today. All right, there we go. I'm going to zoom fit just so I can see the function better. And now I'm going to hit trace and still doing what I said, but I wasn't ever going to find 9.6 and get the right value of x. So I'm scrolling over until y is about 9.6. Oh, my y value is going up there. All right, so trying to find where y is about 9.6. Here we go. Okay, so 9.57, or if I go back one, 9.69. Okay, so what is the x value approximately? The x value is approximately 14. So that means that in 14 years, the price of the car will be about $9,600. So x is approximately 14, so 14 years. Okay. All right, so let's do this next example, which I think is the last one. In 2000, the population of a city was approximately 1.04 million. During the next 14 years, the population increased 2.05% per year. Write exponential growth model. Estimate population in 2008. When will the population be 1.3 million? All right, so the exponential growth model. All right, so we know that we want to use y is equal to a times the quantity 1 plus r raised to t. Okay, plus because it's growth. All right, so filling in what we know. Okay, the initial was 1.04 million, right? In 2000, the population of a city was approximately, so that's your initial. And then it says that during the next 14 years, the population increased by 2.05%. So that's your R value, but you're going to want to turn that R value into a decimal. I mean, I know it's already a decimal, but not a percentage, right? So you're going to move the decimal place 2 places to the left or divide by 100. So you're going to have 1 plus 0.0205 raised to the t. And we can go ahead and simplify what's inside the parentheses. So you have y is equal to 1.04, and then inside the parentheses, 1.0205 raised to the t. Okay, so again, now you can say that this is b, and when b is greater than 0, we know it is exponential growth. All right, so that is part 1. Okay, that's your exponential growth model. So let me just write that up here and erase all my other work. So I have y is equal to 1.04 parenthesis 1.0205 raised to the t. All right. Next it says, estimate the population in 2008. Okay, so that's your time, right, in 2008. So how many years, you're not going to put 2008 in for T, you're going to say how many years passed from 2000 to 2008. That's 8 years. So we're looking at the population over an 8-year time period. So you're going to plug in 8 for T. Okay, so plugging in 8 for T of y is equal to 1.04 1.0205 raised to the 8th. Okay, so go ahead and grab your calculator. All right, so we quit the graphing part. All right, so I'm going to plug in 1.04 and then in parentheses 1.02. Maybe that's why I can't click when there's writing. 205, close parenthesis, raised to the 8th. Okay, and you get approximately 1.22. Let me write that down. So y is approximately 1.22, and we're talking population, right? And it's in millions, so the population is approximately 1.22 million. And you can see if the population 2000 was 1.04 and now in 2008 it's 1.22 million, it did grow, which it should since this is exponential growth. All right, and then the last part of this problem says, when will the population be 1.3 million? So now do you plug in the 1.3 for the t or the y? You're going to plug it in for the y. So you're going to have, can I not write down there? I can't. Okay, so let me erase this. I have to write higher because I'm running out of room below. So you're going to write for this last problem here, 1.3 equals 1.04 times 1.0205 raised to the t. So again, we don't yet know how to solve this equation when the variable that we're solving for is stuck up in the exponent. So at this point, we're just going to use our calculator. So use calculator. So we're looking for, a y value of approximately 1.3. What is the x value? Okay, the x value is going to represent the time. Okay, so pull out those graphing calculators one more time. Oh, I didn't want to make that big. Let me erase this. Okay, so I'm going to go to graphing, y equals. I'm going to type in the function. So it's 1.04, then parentheses, 1.0205 raised to the x, 1.0. I'm double checking this time since I've made so many mistakes trying to graph the last one. I'm going to hit graph. Probably going to have to change my window or do zoom fit again so that the calculator fits this function. There we go. All right, and then I'm going to trace it. So hit that trace button, and you're looking for a y value of 1.3. Right now I'm at a y value of 1.17. So let's see, go up a little bit. 1.3 is the y value I'm looking for. And right there. Okay, so 1.3, that's pretty close, right? 1.29 if I go up one more. So when x is 11, right, that's when the population is approximately 1.3. So let's translate that into an answer for ourselves. So where can I write? When x equals 11, y is approximately 1.3. So that means 11 years after 2000 is when the population is 1.3 million. So 11 years after 2000 would be 2011. So in the year 2011, the population is approximately 1.3. All right, that is finally it for that lesson. Sorry, it was a little crazy with some of the graphing problems. I was having trouble with my technology. But that is it for day one, and I will see you back here for day two.